Now we look at some important properties of cumulative distribution function CDF. In the previous class we defined the probability function and the cumulative distribution function. Let us see some important properties of the function. So here x is a random variable, then the CDF is denoted as fx of x. So which is equivalent to probability of x less than or equivalent to. The first important property is this fx of minus infinity is obviously equivalent to 0. Why? Because the probability of x less than or equivalent to minus infinity will be 0. And fx of plus infinity, so it includes all the points, so it will be 1. Because the probability, the CDF, the cumulative distribution function, is lying in between 0 and 1. It is a non-decreasing function lying in between 0 and 1, and it is a non-negative function. That is, fx of x must be non-negative. Why? Because it is the probability, definitely it must be a non-negative function. And we can write this fx of x of a particular random variable is lying in between 0 and 1. And then if x1 is less than or equivalent to x2, then you can write this fx of x1 is less than or equivalent to fx of x2. So this particular property indicates that the probability, the cumulative distribution function is a non-decreasing function. The significance of this property, that is this condition, indicates a non-decreasing function. That is, CDF is a non-decreasing function of x. Understood? And another important property is the cumulative distribution function of a random variable is continuous from right. That is, fx of x is equivalent to fx of x plus epsilon when limit epsilon tends to 0. That is, you can write it as when epsilon tends to 0, fx of x is equivalent to fx of x plus epsilon. That is, the CDF is continuous from right. So this we can observe. That is, if you see the probability density function that we already plotted in the previous class, we considered a discrete random variable and we plotted its probability density function. So from this it is very clear. That is, fx of x is equivalent to fx of x plus epsilon. Take for example the value at 3, fx of 3, and that will be equivalent to fx of 3 plus some epsilon, because it is continuous from right. So that is, the value at 3 and that is just before 3 is same, is it? Here what is the value at 3? That is 1 by 36. So before it also 1 by 36, and just after 3 it is raised to 1 by 2. So that's why the CDF is said to be continuous from right. Is it clear? So these are the important properties of the CDF, and this is very clear. And the second property is also, and the first three properties are from the axioms. And this fifth property can be verified, or it is through observation. Now we try to prove the fourth property of the CDF. So in order to prove that, so let us consider this is the real axis and this x indicates the values that are taken by the random variable x, and assume this is x1 and this is x2 because we are letting x1 is less than x2. So we have written the condition x1 less than or equal to x2. So here I have chosen x1 x2 in such a way that x2 is greater than x. So definitely this interval can be written as an event in which the random variable x can take the values between x1 and x2. And if you consider this interval that is below x1, that can be written as random variable x is taking the values less than or equivalent to x1. See, here x1 is not included, but here the x1 is included. Similarly, if you consider this portion, it is x is taking values less than or equivalent to x. So obviously, we can write this x1 less than x less than or equivalent to x2 is the event in which the random variable x is lying in between x1 and x2. This is equivalent to if you take the union of this event with x less than or equivalent to x1, this will be equivalent to x less than or equivalent to x2. Is it right? See the diagram that I have drawn, from that it is very clear. The event x1 less than x less than or equal to x2 union x less than or equal to x1 is equivalent to x less than or equivalent to, that is x less than or equivalent to x2 is including these two. Is it clear? Therefore we can write these two events union as x less than or equivalent to x2. Then take the probability on both sides. So if you take the probability on both sides, you can write probability of x less than or equivalent to x2 is equivalent to probability of x1 less than x x2 plus probability of x less than or equivalent to x2. Is it right? Why? Because the two events x1 less than x less than or equivalent to x2 and x less than or equivalent to x1 are disjoint events. So what is this value? This is fx of x2 and this is probability of x1 less than x, this one, and this is fx of x. So this implies probability of x1 less than x is equivalent to fx of x2 minus, but if you observe this, what is this quantity? What this indicates? Which is the probability of a particular event. The probability of an event must be, so therefore this must also be greater than or equal to. Then fx of x2 greater than or equivalent to fx of, that indicates the probability density function is a non-decreasing function. That is, you can easily identify whether the given function is a cumulative distribution function or not, because it needs to satisfy the properties that we already studied, and it must be a non-decreasing function. So we have written 5 properties. Can you expect what is the 6th property that I am going to write? The 6th property of the CDF is probability of the random variable x that is lying in between x1 and x2 can be calculated from the CDF. This is from this equation. What this indicates, if you know the CDF of a random variable, we can find the probability of the random variable x that is lying in between x1 and x2, including x2, excluding x1. That is, this interval can be written as x1 is open one side and closed another side. This event can be indicated like this. Okay. So these are the some important properties of a cumulative distribution function. Now let us represent the CDF in terms of unit step functions for a discrete random variable. So let us assume this x is a discrete random variable and it is taking the values x1, x2 and so on, xn. Then the CDF can be written as sigma I equivalent to 1 to n f of xi u of x minus x. Why this expression? If you observe the discrete random variable in the previous example, we already plotted the CDF, which is a stair-step function. Therefore, that function can be represented in terms of unit step functions. So, in general, a discrete random variable can be represented like this: fx of x, I equivalent to 1 to n, f of xi, u of x minus. Is it right? We check it whether this is correct or not. So, for that purpose, we consider this sample space. Let the coin tossing experiment, the simple example, and let us assume x is taking the values 0, 1 and 2. That is, x is taking the number of x or number of x. So therefore, the values that are taken by the random variable are 0, 1, 2. So this can be x1, x2 and x. Is it? So it is a discrete random variable. What is f of x1 for this case? F of x2, f of x3. This is 1 by 4, 1 by 2, and this is 1 by 2. And we already know that this fx of x is equivalent to 0 for minus infinity less than x less than 0, and this is 1 by 4 for 1. So 1 by 4 plus 1 by 2. How much? This is from 1 to 2. This 1 for the remaining values. Is that right? This is a CDF which is evaluated from the probability function. F of x is a probability function. Fx of x is a cumulative distribution function. Now let me plot the fx of x. Fx of x, here x is taking 0, 1, 2 values, and this is 0 for minus infinity to 0, and from 0 to 1 it is 1 by 4, is it? And between 1 and 2 it is 3 by 4, and from 2 to infinity it is 1. Therefore, it is raised to 1 by 4 here, it is raised to 3 by 4 here, and it is raised to 1. So it is a non-decreasing function, and lying in between 0 and 1. Fx of x is greater than or equivalent to 0. All the properties are satisfied, and you can see that it is continuous from right. That is, fx of x is equivalent to fx of x plus epsilon, where epsilon is a small value. Okay. Now, I try to represent this fx of x in terms of unit step function. So further consider that this is one function, this is 0, this is 1, 2, I have another function. This is also taking the values to let it be x, and this is also x. And consider the third one. Say 0 is a 1, and here I take this function whose value is 1 by 4 for x greater than or equal to 2. What we call this? This is 1 by 4 u of x. Is that right? And next I take another one which is constant equivalent to 1 by 2, okay, from 1 onwards. Therefore, this can be written as 1 by 2 u of x minus 1. Now I take one more function which is constant, that equivalent to 1 by 4 for x greater than and 0 for x less than. This can be written as 1 by 4 u of x minus 2. Now we take this one, and this. If we add these three, can we get this? Verify. See, if you add those functions, see, for x less than 0, this is 0, this is 0, and this is also 0. It is 0. From 0 to 1, this is 1 by 4. This is 0. This is also 0. You will get 1 by 4. From 1 to 2, this is 1 by 4. This is 1 by 2. We are getting 3 by 4. Okay. And for x greater than 2, this is 1 by 4. This is 1 by 2, and this is 1 by 4. You are getting 1. Is that right? So therefore, this fx of x can be written in terms of these. If you add these three, we will get fx of x. Now, can I write this fx of x as 1 by 4 u of x plus 1 by 2 u of x minus 1 plus 1 by 4 u of x minus 1. This can also, see, what is 1 by 4 in this problem? F of x1. Is it? U of, can I write this as x minus 0 plus 1 by, what is 1 by 2 here? F of x2. Therefore, this is f of x2 u of x minus 1 plus 1 by 4 is f of x3. So, u of x minus 1. See, what is this value? 0. 0 is x1. This value is x2. This value is x3. See the previous slide, or see, we defined x1 equivalent to 0, x2 equivalent to 1, x3 equivalent to. So therefore, can I write this as sigma I equivalent to 1 to 3 f of xi u of. Is that right? Therefore, for a discrete random variable, the CDF can be represented in terms of unit step functions. So therefore, in general, what you write, you can write this fx of x for a discrete random variable can be written as sigma I equivalent to 1 to n f of xi. What is f of xi here? Probability function. Okay. This can also be written, so 1 to n. What is f of xi? Can I write it as probability of x equivalent to xi u of So this equation is very important, where we represented the CDF in terms of the unit step functions for a discrete random number. X is discrete. So here we represented this fx of x in terms of unit step function. I think you already know this definition. U of x equal to 1 for this is the basic mathematics function or basic function that we use. So now we look at another function called as the probability density function. Which is called as the PDF. CDF, Cumulative Distribution Function. The PDF is the probability density function. Right now, let x is a random variable. X is a random variable, and fx of x and fx of x is differentiable, and fx of x is differentiable, then dfx of x dx, that is the derivative of CDF, is denoted as fx of x, and we call it as the probability density function. As the probability density function of the random variable x is the derivative of the CDF. That is, if you know the CDF and if the CDF is differentiable, we can find the PDF. See the notation. Okay. So here we are using small f, and this capital X is a random variable. X is the value that taken by the random variable. We are following this notation. Better you follow the same notation. So we see some important properties. This is the probability density function. We already know that this fx of x is a non-negative function. For validity of this fx of x, this must be also a non-negative function. That is one important property. We can check whether the given probability density function is valid or not by verifying this property. That is, fx of x must be non-negative function of x. The second important property is the area under the probability density function. Area under probability density function is equivalent to unity. Integral minus infinity to plus infinity fx of x dx is equivalent to 1. If you know fx of x, we can find the CDF by integration. So here we use a dummy variable, because after integration substitute the limits, then it will be a function of x. Okay, left hand side is a function of x, right hand side is also a function of x. And the probability of random variable x1 less than x less than or equivalent to x2 is equivalent to integral x1 to x2 fx of x dx. See, in the previous case, that is while studying the CDF, we can find the probability of the random variable x lying in between x1 and x2 in terms of fx of x. So here we can write this as x1 to x2 fx of x dx. We already know that this is equivalent to fx of x2 minus fx of x. Yes, is it clear? Now let us see this property. Here integral x1 to x2 fx of x dx is equivalent to fx of x2 minus fx of x1. Is it right? So if you let x1 is tending to minus infinity, x2 is tending to plus infinity, then integral minus infinity to plus infinity fx of x dx is equivalent to fx of plus infinity, and this is fx of minus infinity, which is equivalent to 1. Understood? That is the property. And what about the third one? Third one can be from this. If you integrate this equation on both sides, you will get CDF in terms of the PDF. And how can you prove this? Prove the fourth property. See, this is the proof of the second property. Prove the fourth property. How can you prove it? Take this one, probability of x1 less than x less than or equivalent to x2. So this can be written as fx of x2 minus fx of, this we already proved, is it? See, fx of x2 can be written as integral minus infinity to x2 fx of lambda d lambda. Is it right? See the previous equations. Understood this? And what is this? This value is x1 to x2 fx of lambda probability of random variable x that lying in between x1 and x2 is equivalent to integral x1 to x2 fx of lambda d. Is it clear to you? See, if x is discrete, we can write fx of x as sigma I equivalent to 1 to n probability of x equivalent to xi, just now we proved this, u of x minus x. So from this, what is fx of x for a discrete random variable? The derivative of it this is how much? 1 to n probability of x equivalent to xi is a constant. The derivative of u x of x minus xi is the derivative of unit step function is the unit impulse function. So here to take du of x dx, which is equivalent to delta of x. So here we have du of x minus xi is equivalent to delta of x minus xi. In case of discrete random variable, the CDF can be represented in terms of unit step functions, and the PDF can be represented in terms of the unit impulse functions or weighted impulse functions. Understood that? Is it clear to you? Write down a discrete random variable x is defined by the CDF. X is defined by the CDF fx of x which is shown below. Plot the probability density function. Plot the probability density function. Plot the probability density function. Do this. So this is, I told that this is a discrete random variable, but it is not discrete. It is a continuous random variable. Why? In case of discrete random variable, as we already seen, the CDF has abrupt discontinuities at different values of x. So therefore, this is an example of a continuous random variable. You have to find this. Plot this. First find fx of x and plot it. Can you do this? Try it. A continuous random variable x is defined by a continuous random variable x is defined by the probability density function. A continuous random variable x is defined by the probability density function as fx of x is equivalent to k e power minus 5x u of x. K e power minus 5x u of x. Find the value of k.